Okay, it's recording.
It's recording?
Yeah.
Okay, here, let me toast you.
The camera? I think I have low blood sugar.
What's
I
that?
think I have low blood sugar.
You have a what question?
Low blood sugar.
You have low blood sugar?
Yeah.
We're gonna do something about that.
Thanks.
You could have asked me though, do I have low blood sugar?
Do you?
Well, I meant you.
Does he?
Okay, anyway, I put more of my notes for chapters 5 and 6 on the web page and forgot to get them from the printer. Hold on. Okay, I think unless you have some questions about chapter 5, I think we'll skip and go to Feynman diagrams. I think we've had enough of this gamma purgatory. Dyson invented a way of describing what, in simpler terms, what Feynman was doing. And in fact, the story, I think, is that the two of them got in a car and drove from Cornell to Albuquerque, or from Albuquerque to Caltech, I don't know. Anyway, they drove across the country together. And basically what we're dealing with here is a time-ordered the time evolution operator in the interaction picture. And in this interaction picture, the fields in V of t have free field dependence. The fields in V of t. And that is to say, V of t will be an integral over space of some interaction Hamiltonian density. So the free part, the standard Hamiltonian of the standard model, apart from gravity, of course, is a space integral of a quadratic form in the fields. That's the part that, together with the Higgs mechanism, gives you a quadratic form in fields of specific masses, and that's the what you have then is basically a harmonic oscillator for every momentum mode of every mass eigenstate of every field, and so you have just harmonic oscillators in the boson. Fermions, you just have either for each momentum, you either have no particles or one particle in each momentum and spin state. This H is a sum GI, HI. So in other words, this of T and X is this of T and X. And these H's are typically polynomials in simple models like the standard model, which is not really simple. Anyway, these things are polynomials in the fields, and in the standard model they're cubic or quartic polynomials in the fields. And of course a generic field is a sum over S, an integral dq p pi to the 3/2, and then UL of PS and N, I'm putting N represents the kind of particle. I've normally suppressed it, and I will normally suppress it, but sometimes it's useful. Plus VL of PSN. Let's see, what did I? Maybe I'll use I'll revert here to Weinberg's notation completely, which is like that. So C means the conjugate particle, the antiparticle. And this thing is a bit redundant here, so if we have a C here, we shouldn't have another C there. Okay, so what we're talking about is the S matrix, which is the amplitude for a certain number of incoming particles to become a certain number of outgoing particles. And so this is, I'm just going to write it as A. It's the amplitude for P1 prime dot S1 prime, N1 prime, dot dot dot, PK prime, SK prime, NK prime. And here P1, S1, N1, P1, S1, N, well, capital N in this case. So this is the initial state, the amplitude for the initial state to become the final state. And I guess what I should have done was stick a little, the unitary operator that gives you the amplitude is called the S matrix.
Why is it like shiny on one side with like things?
This was just to show you that this is the amplitude for a certain number of particles coming in, a certain number going out. So N going out, in fact, this, yeah, we've got too many N's here. What did I use in the notes? Oh, I used K. That was a better choice. And so that's K prime, actually. So we have K particles coming in and K prime particles going out. But the standard case, of course, in general, what we're talking about is two particles going in and 2 or 3 particles going out. That's the typical, that's the archetypical thing that one calculates almost always.
Are those all supposed to be subscript K subscripts on the last, in the ket, in the last things in the ket? It's P1, S1, should all be sub K?
No, you're absolutely right. Yes. Whoa! Okay, so this this thing is called the S matrix, and back. Oh, that's a tangent. Let me try to avoid tangent. Now, what is this thing? Well, this amplitude, which is then, as I said, P1 prime is 1 prime and 1 prime, dot dot dot, PK prime prime, SK prime prime, NK prime prime. This whole thing is then time-ordered exponential minus I integral h of x d4 x, and then the initial state, which of course is P1, S1, N1, PK, SK, NK. So that's what we're talking about. And now this thing is related to the vacuum, and it's A of pk prime, sk prime, nk prime, dot, 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 a of p prime 1, s prime 1, n prime 1. And then this time-ordered product is going to be a sum. You expand the exponential, and so it's a sum. Capital N equals 0 to infinity minus I, the capital N factorial integral d fourth x1 d fourth. Actually, since I switched to k, oh, that's right, these n's took the variable in out. D fourth xn, time-ordered product of h of x1, h of xn, and then a dagger of p1, s1, n1, a dagger of p, k, sk, nk. So that's what we have in general, and of course, you'd need a computer program to compute this to any kind of high order. One of the curious things about quantum field theory is it looks sort of infinitely complicated, and it's puzzling the way it becomes so complicated, even though we started just with a theory that's consistent with special relativity and quantum mechanics. And so the mathematics has kind of gotten out of hand. What I should say to begin with is, first of all, we're going to normally order the each term in the interaction. Normally order means you move the annihilation operators to the right and then the creation operators here. In other words, we arrange that everything is written in this kind of order with annihilation operators to the right. There are some disadvantages or ambiguities associated with that, but let's just, it's the standard thing that you do, certainly with, at least initially, with the interaction terms. If you don't do that, then you build infinities in at this stage. On the other hand, this expression here is not normally ordered in any sense, because you have annihilation and creation operators for each kind of particle in each interaction term. And to make matters worse, you're integrating over all of space-time in all n variables, and then you're time ordering it, so you're moving things around anyway. And so if you try to normal order, then times would change, the time ordering would shift things. So it can be kind of confusing, of course. So what you do, of course, is you take advantage of you use the commutation relations to normally order the H's, and then what you do is you normally order this structure. In other words, you move the annihilation operators to the right, you move the creation operators to the left, and you even do that with the annihilation and creation operators that make the initial and final states. So you have this enormous procedure, enormous procession of I mean, you can think of it as a procession as elaborate as Princess Diana's wedding. Some of you people are too young for that. So who's the latest princess to get married? Whatever. Anyway, so you have this enormous procession of annihilation and creation operators, and each time they cross, you use the commutation relation that this is equal to plus for bosons minus for fermions, the thing in the opposite order. Plus delta cubed of p minus p prime, delta s prime, delta n prime. And then, of course, you also have to, if you have annihilation operators crossing, or creation operators crossing, then you have AA prime equal to plus or minus A prime A, and A dagger, A prime dagger equal to plus or minus A prime dagger, A dagger. So you have those rules, plus for bosons, minus for fermions. So that's what you do. And of course, you might say, well, why are we doing this enormous moving around of annihilation creation operators and making everything so complicated? Well, the reason is that the whole thing simplifies when you do that, because A of Psn on the vacuum is 0, and from the left, a dagger of Psn is also 0. So a creation operator annihilates the vacuum when it's on the left, and an annihilation operator annihilates the vacuum when the vacuum is on the right. So that's the whole logic of the thing. And once I've said that, then basically there are no more new ideas. You just have to carry out this enormous procedure. Yes?
Whenever you normal order though, do you keep the delta functions? Do you keep these delta
Well,
or
it
do you
depends
throw
on
them?
where we are. We normally order this and forget about the delta functions.
Yeah.
But then here, we have to keep all these terms. And in fact, if we didn't keep those terms, every amplitude would be 0,
Okay.
as it would be, say, in classical physics.
Okay. So you first go through a normally order and you throw them away. The second go through.
Right.
Keep them. Gotcha. All right, so when you're done, what you have is you have 10 integrals over space-time, but then each of these guys is a cubic or quartic polynomial in fields. Each field is an integral over momentum and a sum over spins. So basically you've got you've just got, I mean, frankly, what you've got here is n, and then you have 3, and that 3 means at the very least you have a 9-dimensional momentum integral in each of these. So a 4-dimensional space integral. So you have you're integrating dx to the 4n dp to the 9n. So that's the integral you've got. You've got a very high level integral. 4n, so it's a multiple integral of dimension 4n and 9n. So if in the simplest case n is 2, so this is 8 plus 18, which is, so it's a 26-dimensional integral effectively, unless I'm somehow screwed up. Now, what saves us is Dirac. Dirac saves us, otherwise we'd be dead. And Dirac saves us because of the Dirac delta function. And so what happens is each of these four-dimensional space-time integrals will turn into a four-dimensional Dirac delta function of momentum. And that will cut things down. And then also apart from that, you will have delta functions when you have annihilation operators here coupling with or pairing with creation operators there. That will give you a three-dimensional Dirac delta function. And similarly, a creation operator from here will pair with an annihilation operator here. That'll give you a three-dimensional delta function. So you've got all sorts of Dirac delta functions helping us out. Okay, now, so what basically can happen, Weinberg describes these things first in terms of rules in space-time, and then in terms of rules in momentum. The momentum space rules are what are conventionally called the Feynman rules, or the Feynman, which lead then to Feynman diagrams. So let me try to describe what's going on. You can have, first of all, a commutation or a pairing between a particle in, say, the final state with a field adjoint, in other words, a psi dagger in one of these interaction Hamiltonians. And what will this be? Well, there you see this psi will, if it's a dagger here, then you'll have a star, a minus sign, a dagger, and then the commutation relation AA dagger will give you a delta function. So this, then the delta function will cancel the integral over momentum and the sum over spins, and what you're left with is simply U star sub L of P prime, S prime, N prime, E to the minus I, P prime dot X over square root 2 pi cubed. So that will be that, and in fact that will be written in a space-time diagram. It will look like this. It'll be an arrow going up. Weinberg likes to do time going up. Most other people do time going to the right. Some do time going to the left, reversely. Anyway, so that's one picture. They even have an antiparticle.
Where did the commutator come from in the first place?
Say it again?
Where did the commutator come from? Like,
it came from
some term in this integral? Or?
Yeah. In other words, part of the procession is you take one of these annihilation operators and you have to move it through all these things till you get to till it annihilates the vacuum.
I see.
And as it goes through here, it goes ka-chink, ka-chink, ka-chink with each of these H's, and in each H there might be a side dagger, which would couple in that way. Another way it can happen is that it goes through all these and then it has to interact with one of these. But that would be a trivial thing if it pairs with one of these, because that just means you got some particles that go through and don't scatter at all.
Okay. And so why is this scattering here? This P prime going up?
Well, P prime going up, but it came from an interaction down here.
Okay.
And what we
I'll draw some arrows on the board, and then what happens in the real case is those things all get joined.
I see.
Okay, so the second is, suppose you have an antiparticle in the final state, and so say a conjugate P prime, S prime, N prime, and this would pair with psi L of X, and then what we would get would be...
Kevin,
Yeah.
what is a conjugate? I don't think I've seen this before.
Oh, all right, well, I'm giving in and using, maybe I shouldn't have, maybe I should have just stayed with my notation, which was simpler. The C just means, is what I was using for B. In other words, if we use my way of doing things, then this would simply be B dagger. And I would have suppressed the N completely. And so this would be B.
All right.
And so this is VL of P prime, S prime, N prime, e to the also minus I P prime dot X prime over root 2 pi cubed. And this one is written this way. So let's maybe write it as P double prime. So the idea is that a final state antiparticle, we put the arrow as if it were going backwards in time. This is an imaginative description that Feynman introduced in some paper back probably in the 40s or 50s. And then, of course, you can have a particle in the initial state that pairs with a field in one of these, and then what you have is psi L of X, a dagger PSN, and this gives you UL of PSN, e to the I P dot X over root 2 pi cubed. So this is psi in one of these that has an annihilation operator that pairs with that and gives you that gives you a delta function, and then that delta function, after you integrate it over momentum in some delta spin, gives you this expression over there. So these notes are on the class webpage. So the next possibility is an antiparticle in the initial state. And if I use my notation instead of Weinberg's, then it's P prime, S prime, N prime. Well, actually, that's nobody's notation. I just skipped a line by mistake. Hold on. So here it's psi L dagger of X with B dagger of PSN minus plus. And so this is VL star of PSN e to the I P dot X over root 2 pi cubed. And just wondering if I have the sign right there. No, I don't think. Okay, let's just see. Psi L. Yeah, that is the right sign. And so how are these two described, these last two? These last two are described by, this is the particle in the initial state, and this is antiparticle in the initial state. And the idea here, they're coming out of some blob And these guys are going into some blob. And then finally, there's the case where you have a particle or an antiparticle in the final state that couples with a particle or an antiparticle in the initial state. And these are just particles or antiparticles that go straight through and are essentially ignorable. You basically, in most cases, you completely ignore such terms and they never even enter into the picture. But then there's one more case that we'll have to examine in more detail, and that's when an annihilation operator here, say, pairs with a creation operator in a different interaction. And that will be an internal line. And so that will be a line inside the blob. And in fact, the way to write that line typically is horizontal. That's the more intelligent way to write the line. So you can write the line like that. And those internal lines are called propagators, and we'll talk about them next Tuesday, or maybe at the end of the hour. I'm not sure if we'll get to it or not. Maybe I should write down what that, numerically, what that expression is. It's a theta function times the psi L plus of x, a psi m, plus dagger of y, commutator or anti-commutator, plus or minus a theta of y0 minus x0 times the adjoint of the negative frequency part of m at y with the negative frequency part of psi L at x minus plus, and that sum is by definition the propagator, which is written as minus I delta Lm of x and y. We'll have more to say about this later. And in fact, it was Feynman's advance, one of his many advances was to write that propagator as a way that was manifestly Lorentz invariant. Previously in perturbation theory, people had just carried over the perturbation theory from quantum mechanics, and it was basically time-dependent perturbation theory, and it just didn't have, well, it was clunky, and it didn't have any, it wasn't obvious whether you had Lorentz invariance or not. Once again, plus or minus here is bosons or fermions. And the next thing is you integrate over space-time, n space-times, and do the momentum integrals and the sum integrals, and then eventually things, what you have left is the amplitude. Now, there is, in the expansion of this exponential, you have minus I to the n over n factorial. In most cases, this n factorial cancels because you have, when you start doing these pairings, you can do the pairings in different ways. For example, suppose you have a particle in the initial state. Well, it could be annihilated by by h of xn, or it could be annihilated by the analogous field in h of x1.
And so you've got n factorial choices for that. And what happens is typically the n factorial cancels. On the other hand, sometimes it doesn't. Then another thing is that if you have a field, an interaction that might be phi cubed, well, if you have a particle in the initial state, there are three choices for which phi can annihilate that particle. And then there are two particles left over, or two fields left over, and they perhaps are creating two final state particles, and you've got another choice of which of the two remaining fields creates which of the final state particles. So what one often does is one writes 1 over 3 factorial, or one writes 5 to the 4th over 4 factorial. So that's to cancel these extra factorials. And then, of course, sometimes the factorials don't cancel. Frankly, the factorials are reasonably easy to keep track of, and the best thing to do is decide how you're going to write the interaction Hamiltonian, and then just see what happens when you carry out this procedure. If you actually do this more than a few times, you then acquire some experience and you develop your own way of doing it, and it's not an issue. What is more puzzling is the minus signs introduced by because you have anti-commutators with fermions, and so you have a minus sign here, and keeping track of those minus signs can be confusing. But again, after you've done a few examples by yourself, you develop some experience and intuition, and then these problems go away. Yeah.
Why does phi 3 give you interactions?
Why what?
Why does phi to the 3 give you interactions, like self-interactions?
Why is it an interaction?
Yeah. And
Well,
it's
okay.
interaction.
Great question. Let's just imagine we have two particle to two particle scattering.
Yeah.
Okay? So let's have these two particles go in, and suppose they're both absorbed at a particular vertex, and then there's another vertex over here. Suppose these two guys come out of that vertex, and then you can have one go across, okay? So in other words, two fields annihilate the two incoming particles. Two of the fields here annihilate two of the outgoing particles, so maybe I should write that as so this is maybe pk, momentum pk, momentum p prime, k prime. And then there's an extra field here and an extra field there. Well, this field and that field pair, in other words, an annihilation operator, you take the annihilation operator from one field and move it through to the right. When it crosses the field that's in this vertex, you get a delta function, and that's what you represent by the line.
So why is it phi to the 3?
Huh?
So why is that phi to the 3?
Well, you had three fields here.
You're saying there's
Three
lines that
fields,
lead
so
to those points.
one field annihilates the particle with momentum p. The second one annihilates particle with momentum k prime, k. And the third one produces a particle that would become final state if it weren't for a field in the second interaction that stops it. And then the other two fields here create a final state bosons of momentum p prime and k prime. But you see, you integrate over all space-time. So this guy could be producing the particle that's annihilated over here. So you don't know whether, both things occur. There's in other words, this process occurs in two ways. The two particles annihilated and shooting a third particle over, and then that interaction sending two out. Or two particles come up, this guy sends one over, everything's canceled here, and then the remaining two fields send out those two particles. And you add the two. And that's what gives you this thing. And in this case, since we're talking about bosons, you just have the plus sign and you don't have any minus signs that require careful thought.
Professor, apparently some structure, why is 5 to the cube?
Why?
Why is 5 to the 3?
Why? Well, I mean, it's you could have in other words, what I'm saying here is that h of x is some coupling constant times phi cubed,
Yes.
maybe over 3 factorial.
Okay.
That's just a particular theory, a particularly simple theory. In fact, it's a kind of crazy theory, because if phi develops a mean value that's negative, this can get arbitrarily negative, so it's not bounded below. So that's so people don't like, so phi cubed is normally thought of as a toy theory that you play with because it's simple. It's phi squared is soluble, and that's the free Hamiltonian. Phi cubed gives you scattering. It's insoluble, but it's the simplest scattering theory. On the other hand, it's unbounded below, so there are crazy aspects to it.
Sure. So, okay, so I guess, is my interpretation right? Thinking phi cubed, you're going to have like a sum of a bunch of products of 3 creation and annihilation operators. And that's sort of what you're drawing here, right?
Yeah, well, let's look at this.
This is like
G
a
over
dagger,
3
dagger.
factorial. It's going to be phi plus phi minus at one place, phi plus phi minus, phi plus phi minus. So this has annihilation operators, this creation operators, annihilation, creation, annihilation, creation. And so the product of those, for example, if they're at this vertex, then you have to use 2 of the phi pluses to annihilate these 2 incoming particles. And then if you do the same thing at this vertex, you pick 2 of the phi minuses to create these 2 particles, and then what's left over gives you what's represented by this line.
Let's see.
So what 5 forward look like?
What does phi 4 look like?
Yes.
Okay, great question. So there, if we were doing two particle scattering, we would have something that would be, let us see, is there anything? In this case, the lowest order term is first order. You see here with phi cubed, you couldn't get a scattering process with only one factor of h. So you need h of x, h of y. Whereas if you have phi 4, then you have kp going to k prime, p prime, and this can occur at one vertex because you've got 4 fields, and so at this vertex, and so 2 of them annihilate the incoming particles, and 2 of them create the final state particles. But then you also go, when you go to higher order, that's g, you get g squared, and now you've got something that's more complicated. You get something like this, and in fact, this is divergent. So that's the sad thing about quantum field theory, is that the first thing you calculate is great, and the second thing you calculate is instantly wrong.
So in this phi 3 term, is that not first order?
No, that's second order.
The diagram that you drew?
Yeah.
Oh, because you have 2,
Yeah, so that's G here and G there.
Okay, you need 2, okay, because you have 2 vertices. So the number of vertices tells you what order, like, I don't know.
Yeah,
Fifth
yeah,
order
yeah.
term, you'd have 5 vertices, I see.
Yeah.
Okay.
Okay, anything else before we go on to? All right. Okay, so, the next theory I'm going to consider is the one that is the first one that Weinberg considers as a toy theory. And it, in fact, is of the same form as the Standard Model. In other words, essentially all the terms in the Standard Model, except for the self-interaction of the Higgs field, are of this form. So this is something that's really worth looking at. Okay, so this is, well, if we really write it in more detail, it looks like this. So these are two fermion fields, and this is a boson field. At least I think that's the one that Weinberg does first. Yeah, fermion boson scattering. Okay. And so, what do we want to talk about? What we want to talk about is a fermion going in, and I'll write it as a dotted line for a boson going in, and then a fermion going out, and a boson going out. The rule is you put an arrow on a line if it's a, it can carry charge, or if it's different from its antiparticle, you don't use an arrow if it's self-conjugate. So this is the thing we want to compute, and it's pretty clear that you have to go to second order because you can't just have three fields produce four particles, absorb two and create two. And this G you can think of as gamma matrices if you want. And in fact, I think what I've done is I've suppressed the L and M because the fields are distinguished by whether it's a joint or not, and whether it's going to be at X or at Y. And so the amplitude is going to be minus 1 over 2 factorial. The minus sign comes from minus I squared. 1 over 2 factorial from expansion of the exponential. And then you have an integral, and I'm going to write it as d fourth x, d fourth y, 0, and A of P prime, this is the annihilation operator corresponding to the final fermion. And then I've written B of K prime for the annihilation operator for the final boson. And this is the fermion. Final state. And then what we're going to have here is time-ordered product of h of x, h of y, and then b dagger of k, a dagger of p back p. So that's what we have, that's what we're trying to compute. And h is just this, and of course it's normally ordered. Normal ordering is denoted by 2 colons. Okay, so this amplitude then is or if I'm going to write the 2 factorial. Oh, I did write it. Okay. G squared
dagger of x, psi of x, phi of x, psi dagger of y, psi of y, phi of y, b dagger of k, a dagger of p, vacuum. Okay, so that's what we're computing. And what you can do is you can just plug everything in and do it, but it's more useful to I see I should have, there's a typo here, let me just get rid of this. So as I said, the 2 factorial normally cancels. In this case, it cancels for a very simple reason. Namely, this boson can be annihilated either by phi of y or by phi of x. And the difference between the two is, I mean, there's just no difference because we're integrating over all x's, and this is a time-ordered product. There's no sense in which the x's stand to the left of the y's. So, the first thing we do then is we write this as minus g squared integral d fourth x, d fourth y, 0, a of p prime, b of k prime, time-ordered product, psi dagger of x, psi of x, and this is going to create the boson that this annihilates. So this will be phi minus of x. I'm just choosing this one to annihilate that boson, and this one to create the boson that this annihilation operator annihilates. So this will be psi dagger of y, psi of y, phi plus of y, e dagger of k, e dagger of p. Okay, then, well, we know what happens. We just substitute for phi plus. So that is minus g squared integral d fourth x, d fourth y, 0, a of p prime, b of k prime, t of psi dagger of x, psi of x, phi. In fact, just save time and space and my shoulder. I'm going to, since we've decided that this will be the negative frequency part, I'm just going to put it in right now, and I'm going to call this an integral d cubed k double prime over square root. It's a spin 0 field, so that was 2 pi cubed k double prime 0. This will be b dagger k double prime e to the minus I k double prime dot x. So there I've just replaced, I've just taken the, this is phi minus at x, right? I think that's right. So then, and it's inside the time ordered product. Then we have psi dagger y, psi y, and now I'm going to take the positive frequency part here. So this will be d cubed k triple prime over the square root of 2 pi cubed 2k triple prime 0 b of k triple prime. And then what's left is the dagger of, oh, I forgot the phase factor. The phase factor for the annihilation operator is e to the I k triple prime dot y, and then b dagger of k, a dagger of p vacuum. So that's that's where we are at this stage. And now, this gives us a delta function of momentum. This gives us a delta function of momentum. In other words, B dagger is B dagger B on the vacuum, which is 0, plus the value of the commutator. And so what we've got, the next thing then is G squared integral d fourth x, d fourth y, 0, a of p prime. Now this is a fermion. I should have included the spin. I've suppressed the spin. Let me put in the spin. S prime. I left that out. B of k prime. Well, B of k prime with B dagger of k double prime, that's going to give us a delta function. And so this is gone, and what we have is T psi dagger of x, psi of x, and now this integral d cubed k double prime over square root of 2 pi cubed 2k double prime 0. But now this is delta cubed of k prime minus k double prime, e to the minus I k double prime psi x. And then we have psi dagger of y, psi of y, integral d cubed k triple prime root 2 pi cubed 2k triple prime 0. Delta cube of k minus k triple prime e to the I k triple prime y e dagger of p 0. Okay, so this these things collapse then, and what we have is minus g squared integral d fourth x d fourth y 0 a of say p prime s prime time ordered product of psi dagger of x psi of x, and these just the integrals just give us phase factors, and these denominators, I'm going to take all the denominators and put them over here. So this will be 2 pi to the 6th 2k0 2k prime 0. And then what's left here is psi dagger of y, psi of y, that's the end of the time ordered product. And we have a dagger of p and s 0. And then the phase factors are e to the I, ky minus I, k prime x. Okay, I think I've got everything there. Okay, I see a huge typo here. Ran out of time when I was latexing all this. Okay. Now we've got to analyze this structure, and this structure is a little bit subtle because it involves fermions. And what we can say is we can consider the case where this field annihilates the incoming fermion. And if that happens, then this field creates the outgoing fermion. But then we also have to consider the other case where this field creates the outgoing fermion, and this one annihilates the incoming fermion, and we have to keep in mind that these are time-ordered products. And at this point, I wish that this had been a scale field, so I didn't have to deal with these minus signs. But, so let's just write them as A is equal to A1 plus A2, And we'll say that A1 is the simple case where this is minus g squared over d fourth x, d fourth y, root 2 pi to the 6, 2k0, 2k prime 0, 0 a of p prime s prime, and I'm just going to do time ordered product psi. Okay, what do I want here? It'd be psi plus dagger of x, psi of x, psi dagger of y, psi plus of y, a dagger of p and s, e to the I, ky minus I, k prime x. Okay, so that's A1. A2 is minus g squared, let me just say ditto, the same thing, ditto, but now it's time ordered product of psi dagger of y, psi plus of y, psi plus dagger. Oh, wait a second, why did I interchange y and x? That was a mistake. Psi plus dagger of y, psi of y, a dagger of p and s, e to the I, k dot y minus I, k prime dot x. All right, so let's look at A1 first, and I forgot this vacuum over here.
Kevin, so you have two terms because you're considering one case where you have the first psi y annihilating a particle, and then you have the one on the very left, the psi x dagger. Or sorry, can you just explain this again? Why you have these two terms and
Unfortunately, the dagger and plus look this way.
yeah.
Yeah, but can you use a different symbol for the dagger?
Well, the point is that
Parentheses.
either this vertex, either this interaction can annihilate the incoming fermion, or this one can. And I'm going to consider them separately and add them together.
Okay. And it will annihilate that one. I don't know. I don't see why the two terms together will annihilate it. I mean, I guess you're picking out like an A dagger from one end and an A from another, or
What we've got is this expression here.
yeah.
And so in this expression, this thing is psi plus of y plus psi minus of y.
Yeah.
And if we pick the psi plus of y, that can annihilate this thing.
Sure.
And on the other hand, over here we have psi plus of x plus psi minus of x. If we pick the psi plus of x, it can annihilate this guy.
Mm-hmm.
And if we let this psi plus annihilate this incoming fermion, then this psi plus has to annihilate the fermion created by this field.
Mm.
So that's how that works.
And you don't have to worry about any of the psi minus terms because you didn't have any antiparticles to begin with. Is that true?
Yeah.
Yeah. Okay. Sure.
the sign minuses are going to show up in the what we have left over is psi of x, psi dagger of y, and then here psi dagger of x and psi of y. Yes.
So y a equals to a1 plus a2.
Y what?
Y a equals to a1 plus a2.
Y is
The-
a equal to a1 plus a2?
The expression doesn't look the same.
They look the same?
No, it doesn't look the same.
Right, so a is equal to a1 plus a2.
Okay. Is that from some commutation relation?
Well, I guess you're right. Maybe I have skipped something.
Why do we care about the time?
Oh, okay, literally, let's see.
In your interaction Hamiltonian, you have hx and hy, right?
Well,
and then they're happening simultaneously. They're not happening at different times.
I hesitate to use the word simultaneous. We've got this time-ordered product here. What I'm basically saying is that either this field or that field can annihilate this particle. So those are two different possibilities. If this field annihilates it, that's A1. If this field annihilates it, that's A2.
I'm confused about the time ordering operator because on the blackboard over here you have a Hamiltonian that has time and a space dimension, but then here in this Hamiltonian there's only a space dimension unless that's something else. Did I miss it?
See, can you say that again?
Why do we have the time ordering operator if there's no if the Hamiltonian is
It's the Hamiltonian of the fields, and the fields are at a given time, and you integrate over all times.
okay?
I think are you considering x to be like space and time?
Yeah, is X a space
Yeah,
time
x
coordinate?
is d4th x is space
Oh.
and time. So d4th x is dt.
Okay, yeah, because I was confused because on the other board you separated them out into time and space components.
Yeah. Well, that's because the Hamiltonian is an integral over d cubed x of h of x.
Sure, yeah.
Okay, so let's look at this one. Then, and let's do it in a super careful way so we don't screw up, and since I'm already out of notes, so I'm winging this part. So let's just look at what this is going to be. It's going to be A1 equals minus t squared and of course this factor here 2 pi to the 6, 2k0, 2k prime 0. Okay, and then vacuum A of 2 prime, S prime, and then what's left is this time-ordered product. So I'm going to write the time-ordered product explicitly. So this then is beta of x0 minus y0, and that would be psi plus dagger and then the next term is dagger of y psi, well, let's make this dagger look like a dagger. And this is psi plus of y. And then plus theta of y0 minus x0. And now we would have psi dagger of y, psi plus of y, psi plus dagger of x, psi of x, a dagger of p and s vacuum. Oh, and I left out the Fourier factor. And the Fourier factor is maybe I can stick it in the front so it's
Are these thetas heaviside functions or is
all right, hold it one thing at a time. Let me just do this. E to the
are they heaviside?
One is saying that one happens before the other, and the other is saying that the other
Oh, I
happens
see.
before the other.
okay, what was the question?
I was just wondering, are those like heaviside functions? The
What?
thetas, are they heaviside functions?
Oh, yeah, sure. Theta, there's a story about that. I must have told you the story, haven't I? The name of this guy is Heaviside,
And
a
one side's heavy.
mathematician. Yeah, and his function has one side that's heavy and the other side is, in other words, this is 0 and this is 1. And so this is theta of x. It's 0 for negative x, 1 for positive x. So it's just a way of writing the time-ordered product. And Dyson wrote a number of articles in the New York Review of Books, and in one of them he describes some of the interactions between the various people in the Cambridge University math department when Dyson was a graduate student. And it's quite comical. One of the mathematicians was a fervent public Christian, and the other one was an outrageous public atheist. And the atheist was always making fun of the Christian. Anyway, it's best to read it in the NYRB, which is available at UNM for free. Okay, so let's see, what are we going to do now? So, so the thing now is to replace the two psi pluses with their annihilation and creation operators. And in fact, so let's just see, yes, okay. Okay, so this would be minus e squared d4 of x, d4 of y, ddi, ky, minus I, k prime x over this square root 5 to the 6, 2k0, 2k prime 0, and 0 a of p prime s prime, theta x0 minus y0, psi plus dagger. Oh, well, I'm going to write this as psi plus dagger. So this will be an integral d cubed p double prime over 2 pi to the 3/2. And this is psi plus dagger. And so that is u star L of p and s, or p double prime, s double prime. And it's a of p double prime, s double prime, dagger, e to the minus I, p double prime dot, what's the variable, x. Okay, so I think I've done that correctly. That's psi plus of x dagger, right? And next we have psi of x, and then we have psi dagger of y, and then the next term is psi plus of y, and so this is an integral dq p triple prime over 2 pi to the 3 halves. And this is just a plus, so this is ul of p triple prime s triple prime a of p triple prime s triple prime e to the I p triple prime dot y, and then a dagger of p and s 0. Now, okay, so what I've done here is I've just done the first theta component. We also have to have, so let me do it this way, plus 0a, well, I guess instead of writing that twice, what I might as well do is just say, well, I've already got the, all right, I've already got the square bracket there. Okay, the next one is theta of y0 minus x0. And now, what we have is psi dagger of y. But now the psi plus of y, well, that's this term over here. So that's, let us just say dq p double prime 2 pi to the 3 halves ul of p triple prime s triple prime a p triple prime s triple prime e to the I p triple prime dot y, and then that's times psi plus dagger, so that's this term, which is d cubed p double prime 2 pi to the 3 halves ul star of p double prime s double prime a dagger. Oh, all right, we're out of time basically. So this, actually now I've even lost track. Am I even on the right? This thing, right? I guess so. All right, so this is then psi of x. And so I'll write it that way. All right, that's, one then continues in this way. I'll try to latex this stuff up and put it on the class webpage at some point. In any event, what's left here is going to give us one term in the Feynman propagator for fermions. And then when we do amplitude 2, we'll get the other term in the Feynman propagator for fermions.
It's very impressive, Kevin.
Oh,
I think you did that without notes.
Well, thanks. Not so impressive that I don't need notes. So. All right, let's turn it off unless there was another question.